All right, Fred, ready to do some homework?
Yep.
All right, chapter 3. Number 369. The chemical substance with a natural gas is a compound called methane. So CH4, methane. Its molecules are composed of carbon and hydrogen. So, yep, that's carbon and hydrogen. And each molecule contains 4 atoms of hydrogen and 1 atom of carbon. In this compound, that many grams of hydrogen is combined with that many grams of carbon, carbon 12. Use this information to calculate the atomic mass of the element hydrogen. Okay, so we're trying to find the atomic mass of the element hydrogen. Now, the atomic mass of the elements are on the periodic table, so we know that our number should be pretty close to our 1.0079 there, right, using the atomic mass. Now, what we're trying to see here is that there's a relationship between the mass of hydrogen in a compound, the mass in this compound here, and the mass of the carbon in that compound, and that same relationship exists between the atomic masses that are in this compound.
Oh, I'm not sure I get that.
Well, if I want 1 mole of CH4, I have to weigh out enough to get 1 mole of carbon and 4 moles of hydrogen. So that would be 12 grams for the carbon and then 4 grams for the hydrogen. So if I weighed out 16 grams, so this is for the carbon and that's for the 4 hydrogens. So if I weighed 16 grams of CH4, then I get 1 unit of CH4. Okay, so this relationship, the 12 to 4, should also be a similar relationship in terms of the grams of hydrogen in this compound to the grams of carbon. All right. So if, for example, if I said I have this many grams of carbon for every this many grams of hydrogen, and that's what they're telling us. They're telling us that for every 1 gram of carbon, I have 0.33597, 0.33597 grams of hydrogen. Okay. And then I should say, okay, so that should be equal to this ratio where I have 12 grams of carbon equaling, and they want us to identify exactly what our grams of hydrogen are. But we have to remember that we have 4 of the units of hydrogen. So if I just solve for the x there, that's going to tell me the grams of hydrogen. Okay, and how much the mass of 1 hydrogen is. All right, so we got 12 times the 0.33597, and whoops, what happened there? Let's start over. 12 times the 0.33597, okay, and then that is going to equal, so you do cross multiplication, right? That the product of these two has to equal the product of those two. So if we divide by 4 there, that's our answer there, 1.00791. Okay? Good job.
Oh, I didn't do much.
Sorry about that. I should have asked you a little bit more. All right, so our next one here. We have an element, X, and apparently it forms a compound with oxygen in such a way that, what does it say there, Fred? What's our chemical formula? X, what? I'll put an A down here and a B down here. We want to find the A and the B. Can you tell by reading that problem?
It says there's 2 X's.
X2.
And 3 oxygens.
O3. Very good. So, we want to recognize that there is this relationship that exists between the mass of the X and the mass of the oxygen. That is, if we have 2 X's and 3 oxygens, and that same relationship will exist between the atomic mass of X, of 2 X's, over the atomic mass of 3 oxygens. Okay? And so we can use the periodic table and the mass on there. We can look at oxygen here and see its mass, 16. So I can do this same ratio, 3 oxygens, so 3 16s, right? And 2 I don't know what my mass of my atomic mass of my other element is, but I'm told in the problem here about the mass of these two, right?
Yeah, it says that there's 1.125 grams of X.
Very good. 1.125 grams of X. And how about the mass of oxygen?
That's 1 gram.
That's right. So the law of definite proportions says that in this sample of the material, if it's this ratio, also if it's the same sample, if it was a larger amount of it, but I'll have the same ratio, right? This is the amount due to the oxygen, and this is the amount mass due to the aluminum, using our atomic masses on the periodic table. So I can solve for X here, right? 3 times 16 times 1.125, and then again cross multiplying, and then setting that equal to this. So that's 48. That's 3 times 16, right?
Yeah, I think so.
1.125. That should be equal to 2x times 1, which is just 2x. Okay, so we got 48 times 1.125 divided by 2. So 27, and that's the mass of 27 grams, or the mass of my my element, my unknown element. So I should be able to look here on the periodic table and figure out which element I am looking for. Do you see it?
I think I see it.
Oh, really? I can't quite see it yet.
Aluminum there is near 27.
Oh, good. Yeah, aluminum, 26.98. Excellent. Good job, Fred. All right. 373. If an atom of carbon-12 had been assigned a relative mass of 24 units, what would be the average atomic mass of hydrogen relative to this mass? Okay. Well, there's a couple ways to kind of think about this. But we see on the periodic table right now that the assigned element for carbon is 12, and that the mass of hydrogen, let me bring up the periodic table here. That is not the periodic table. Where is my periodic table? It looks like it's moved. There it is. Okay, so carbon is 12.001. That's the average mass, but carbon is assigned 12, and hydrogen relative to 12 is 1.0079. 1.0079. Well, we're just basically saying that if I take this relationship and compare it to, let's say that somebody had said, okay, carbon we're going to call a mass, or a unit mass of 24, then we could find out what our unit mass of hydrogen's going to be. All right, so solving for X, which will give you a little more than 2 there, right? Okay, good. All right, naturally occurring copper is composed of 69.17% copper 63 with an atomic mass of 62.9396, and then the rest of it is copper 65 with that mass. And we want to use this data to calculate the average atomic mass of copper. You know how to do this, Fred?
Well, I think we just add the two together and take the average.
The two what?
The two masses, so 62.9396.
So you're saying 62.9396, and then add that to our 64.9278.
Yeah.
So if I add those together, do I get the average?
Well, you have to divide by 2.
Okay, so if I added those two together and divided by 2, that would give me the average?
Yeah.
That's true. That would give me the average for these two different numbers, right? But it doesn't say that our material is half this and half that, right? So remember, this is like taking a hat full of our different kinds of copper atoms here. We're pulling them out one by one and measuring their mass because we want to find the average. We want to add them all up and then divide by however many we pulled out, right? And we could do that because these are the two masses that exist in here. Half of them aren't this and half of them aren't that, right? It's a different percentage. It says right there it's 69.17% this stuff, 30.83% that stuff. So if we were to pull this out, then gradually over time we would see 69.17% of the ones we pulled out had this mass, and 30.83 had that mass. Now, how do we take the average of these ones coming out of the hat?
You mean if we pulled them out of the hat, how would we get the average?
Yeah.
You just keep writing down the numbers of each of them, the masses of each of them, and then add them all together and divide by however many you pulled out.
That's right. That's right. Now, that would take a long time to add that all together, right? If I had a list of 62.9396, 62.9396 every time I pulled out one of those, and then these values would be in the list too, right?
Yeah, I guess.
And somebody has already done that apparently, right? Because they have the percentages there for me.
Okay.
So if I just, instead of making a list of every time I pulled it out, I could multiply this by the percentage, right? So it's pulled out 69.17 out of every 100 times you pull out. So 69.17 times it's pulled out. Well, this is pulled out 30.83 times. And again, those are per 100 percentage. So I'd have to divide this all by what?
By 2?
No. I pulled out of the hat how many times?
I don't know.
Well, see, I pulled out 69.17 times this and 30.83 times this. So the sum of these two, which is 100, is what I have to divide by. So that will give me the average percent. Does that make sense?
Yeah, okay.
So let's finish that up on the calculator here. 69.17 times 62.9396. All right, so that's the contribution there. And then we have 30.83 times 64.9278. All right, that's the contribution there. So I'm going to take this one, add it to this one like that, and then I'm going to divide by my 100. Whoops, not my 1,000. And 63.55 is what we're finding is the average mass of, unit mass of our copper. Okay, and then we could also verify that by looking on here, 63.55. Okay, good. All right, so here we have the number of neutrons, protons, electrons in an atom. And we have to give the number of neutrons, protons, and electrons in each of these isotopes. Do you know what an isotope is?
Isn't it like same protons, different neutrons?
Very good. That means they have the same number of protons in a species, in an element, but different number of neutrons. The classic example is like carbon 12. And this is where the number goes when you're identifying the mass number, comparing carbon 12 to carbon 13, and then carbon 13 and 12 to 14. We say that these are all isotopes of each other. So, do you know how many protons carbon has?
We can look at the periodic table, right?
That's right. So you look at the periodic table to find the number of protons. So that's 12. That's pretty easy. Okay? Sorry, that's 6. That number right there is pretty easy. But what is the mass number?
The 12? Didn't we say that that's protons plus neutrons?
Very good. Now remember, you can sometimes you'll see that 6 there. I'll write it there just to remind us. But this is protons plus neutrons. And it's nice to have that protons down there because then we can just see that 12 minus the 6 and we can know the number of neutrons right away, right? So when you say something like radium-226, we look for our atom of radium down here, right? And that has how many protons in it?
88.
Very good, 88 protons. So when they say radium-226, what are they talking about, the 226? Where do we put that? So radium is Ra.
Is that the mass?
That's right. We always refer to the element by its mass if we're trying to distinguish isotopes. So radium-226, and then what goes to the bottom left there?
Was it 88?
That's right, 88. What is that number?
That's the number of protons.
Very good. So how would we get the number of neutrons here?
226 minus the 88.
That's right. Very good. So for lead 206, you can just take the lead. Lead on our periodic table is 82, right? So lead 206, 82 is the number of protons, right? So it's nice to write down the number of protons there. Sodium 23. What's the number of protons on sodium?
Periodic table, please. Okay, 11.
That's right. 11 protons on sodium. So our 11 can go down there. Now, how about the number in carbon 14 we have here? That's on our list as well. Yeah, so that's all of them. Now, how do we identify the number of electrons?
I'm not sure.
Well, the number of electrons is the same as the number of protons if there's no charge. The charge would show up here. So, for example, if I had a sodium with a positive charge, that would mean I have given up an electron. And that's why there's more positive charge. You don't lose or gain protons. So if there's no charge, that means that the number of electrons is the same as the number of protons. All right?
Okay.
You think you can answer those now?
Yeah, I got them.
All right. Iodine 131 is used to treat thyroid because it's radioactive and it will decay and kill. Radioactive decay will kill its surrounding cells, right? So that's one thing. Another thing it does is it's not just used to kill them, it's also used to identify where they are, because you can use isotopes of any element that releases radioactive particles, and then they can be detected. Okay? So we want to know the number of protons, neutrons, and electrons in an atom of iodine 131.
131 is the what? That's the protons plus the neutrons, right?
Right. So we get our periodic table.
Iodine has 53 protons, right?
That's right. So we have 53 protons. 131, that's the protons and neutrons. So minus the 53, and that's our number of neutrons. And what about electrons?
Well, you said if there's no charge. Is there a charge on this?
There isn't a charge. It just says iodine 131. It would have to give us more information if there was a charge. So what does that mean?
It has the same number of protons as electrons. Same number of electrons as protons, which is 53.
Okay, very good. All right, so we want to use the periodic table to write the ions that form from these elements. Okay, so we look at the periodic table here. Potassium. Here's potassium, 19. Potassium is 19.
Okay.
Now, how can we tell what kind of ion it would like to form?
I can't remember.
Well, we say that all elements, this whole batch, like to have electron configurations, meaning they want to have the same number of electrons as the noble gases. The noble gases are stable, and we know that, and their stability is related to the number of electrons that they have. Why is it these numbers? We don't exactly know, but we have models that explain how other atoms can attain noble gas configurations, meaning the same number of electrons as the noble gases. So potassium has 19 electrons, 19 protons to start off with, and it wants to choose to be like one of these noble gases. Which one's very close to it?
Argon has 18.
That's right. So it can't lose protons, but it can lose an electron to have a noble gas electron configuration. All right? So potassium, if it loses an electron, what kind of a charge is it going to have?
Is it going to have a lose an electron of -1?
Okay, so potassium here. If I lose an electron, well, let's start off. How many protons did I say I had?
Periodic table says 19.
So we have 19 protons. I'll draw those protons in the nucleus. There they are, 19 protons. 19 protons. And how many electrons does an atom of potassium have?
I don't know.
Well, remember we said it's the same, right, if there's no charge.
Oh, okay, yeah. So 19.
All right, so 19 electrons. All right, so there's, I won't draw a dot for all of them, but I'll write down here 19 electrons. Okay? If I lose an electron, now what's going to happen? I still have my 19 protons there, right? But now I have 18 electrons. And what's the resulting charge that's going to result when I've lost that electron?
More positives than negatives.
That's right. How many more?
Just one.
That's right. And we show that here, that the resulting charge by losing that electron is a positive charge. So we say potassium wants to form a potassium ion to obtain an electron configuration closer to that of a noble gas. Okay?
Okay, I get it. So bromine, where's bromine?
Bromine's down here, 35.
Does it want to lose enough to become like argon?
Well, you could think of that, but elements don't want to lose too many electrons, and they don't want to gain too many either. So bromine can actually improve its situation if it just gains one electron and becomes like krypton.
Oh, okay, yeah. So when bromine gains an electron, does that give it what kind of a charge?
Well, that's good. Good question. Bromine has, looking at the periodic table, 35 protons, and that means it also has 35 electrons if it's neutrally charged. So if bromine now is going to gain an electron, 36 electrons, the 35 protons are still there, what's the resulting charge?
A negative?
That's right, it's going to have a negative charge. So this is the answer for potassium, this is the answer for bromine. What about magnesium?
Magnesium has 12. The nearest noble gas is 10. So it wants 12 electrons, and that neon has 10 electrons. So it wants to lose 2 electrons.
All right, so what happens, what do we put up here for the charge if it's lost 2 electrons?
Not a -2, because that would be gaining 2. +2.
That's right, a +2 charge because it's gained those 2 electrons. How about sulfur? What does sulfur want to do?
Where's sulfur?
It's element number 16.
Okay, it wants to gain 2 electrons.
That's right, so that's going to be what kind of a charge?
2-.
That's right. All right, and aluminum?
Aluminum is number what?
13.
Let's see. Wants to gain 5. That's a lot. Can it lose some? Oh, it can lose 3.
That's right, and that's exactly what it wants to do. Aluminum wants to lose 3, so the resulting charge is going to be what?
Losing is plusing, so +3.
Okay, very good. Now remember, that +3 charge is an indication of the resulting charge due to the loss of the 3 electrons, right? 3 protons more than there are electrons. Good. All right, so now we're going to write the formulas for the ionic compounds that form between sodium and bromine, potassium and iodide, barium and oxygen, and magnesium and bromine, and barium and fluoride. All right, to do this, we need to look at the periodic table and know what kind of ion sodium wants to form. Can you tell by looking at the periodic table what kind of ion sodium wants to form?
It has 11, it wants 10, so it's a +1.
Very good.
It looks like everybody in that first row would want to form a +1.
That's true. That's true. Everybody in that first row wants to form a +1. And what about this row?
Would they all want to form a +2?
That's right. That's right. And that's kind of a shortcut way to think about it. These all want to form +1 charges in the compounds that they form, and these ones all want to form +2. You want to not forget, though, the basis of why that's the case. Calcium wants to lose those 2 electrons to have a noble gas electron configuration of argon. Okay? So, yeah, that's a shortcut way. And we also have kind of the same way. Everything here wants to form a -1. Everything here wants to form a -2. And everything here wants to form a -3. So that simplifies things a lot.
Yeah. Why do they want to form -1, 2, and 3 like that?
Okay, let's look. So chlorine, because it's here, it's always one away. Whatever's in this halogen column here, it's always one away from a noble gas, right?
Oh, yeah, yeah. Okay, I get it.
Oxygen and sulfur are
2 away.
That's right. Okay, so bromine wants to form a bromide ion. So these come together in a 1-to-1 ratio because every one atom that has a plus, or every ion that has a plus charge comes together with every one ion that has a minus charge. Potassium iodide, okay, Can you see where it's at on the periodic table?
What element is it?
19.
Oh, that's going to be a +1.
And the iodide?
What element is that?
53.
Oh, it's a -1.
Very good. So what is the resulting compound going to be?
Ki.
Very good. Excellent. Next one, barium oxide.
Barium. Where's barium? Barium. Is that 59?
56.
Oh, 56, yeah. Okay, so that's a +2.
Very good. Barium is a +2.
Oxygen is, I see that one. That one's a -2.
Very good. -2. So,
is that 2 bariums and 2 oxygens?
well, you just need them to come together so that the charges balance each other.
So it's just 1?
That's right. So it's BaO.
Okay. Magnesium and bromide.
Bromine, right?
Oh yeah, bromine, but it calls bromide when it's the ion?
That's right. Bromide ion, Br-, we already did that one up there. Magnesium, what's that one?
Where's it at?
Element 12.
Oh, that's a +2.
+2. Okay, so then what?
2 magnesium for every bromine.
Whoops, I should have written this down here.
Oh, no, 2 bromine for every magnesium.
Yeah, right, because magnesium has a +2 charge and there's only 1 bromide. So I need 2 of these bromides to make sure it balances with that. So there, MgBr2 is my resulting chemical formula. How about barium fluoride? What's it going to be?
F is -1. Ba again is +2. So that's BaF2.
Very good. Excellent job. Okay, next problem. So we're going to write the chemical formulas for the ionic compounds that form between these ions, all right, between these ions. Now the ions here have the metal ions, right, have the charge provided already, which is nice, okay? Now a reminder of where the metals are. Everything to the left of our staircase here are metals. Everything to the right are nonmetals, except for this hydrogen is an exception, right? But ionic compounds are compounds that combine metals with nonmetals or metals with what we call polyatomic ions. Polyatomic ions. Now, hopefully you have a periodic table printed out. If you don't already, you should print one out soon. But on the back of the periodic table that I provided are a chart of the polyatomic ions. Okay, so we'll be able to use that for this first one here, because we have the potassium ion, K+, and the nitrate ion. And we're not familiar with the nitrate ion always, and so we look it up. And that's what I want you to do. Every time you need to look up or see a polyatomic ion that you're not aware of, look at its chemical formula and its charge and its name, right? All those 3 things. You want to look at them well, try to learn them. And then gradually, as you do that every time, you'll remember them better than if you just memorize it all at once and then forget it for every chapter in the future. So that's an NO3-. So this is one ion and that's another. And so the ratio is what?
It's just 1 to 1.
That's right. So KNO3 is potassium nitrate. All right. Calcium ion coming together with, what's the other compound? Or the ion?
Acetate.
Do you see the acetate ion on there?
Oh, C2H3O2-.
That's right. Now, this is a +2 and that's a -1.
So we need 2 of the acetates?
That's right. Ca, and now when we have a polyatomic ion with many atoms, right? That's what polyatomic means. I need to go like that. I need to put that in parentheses so that I'm showing I have 2 of all of those ions, or all of those atoms in that ion. Okay, good. Next, ammonium ion and the chloride ion.
Ammonium, is that a polyatomic? Yeah, there it is on the top. So NH4+.
Very good. Right, there's our ammonium ion.
And then Cl-.
Okay.
That's just a 1-to-1 ratio. So NH4, Cl.
That's right.
Do I have to put that NH4 in parentheses?
You don't need to put the NH4 in parentheses because we just have 1 of them. But if you needed multiples of them, you would put it in parentheses. Okay. D.
Iron with the +3 charge.
Very good. That's iron. Did you look that up on the periodic table?
Yeah, I was looking that up while you were explaining it. And carbonate. Where's carbonate?
Okay, so we look at our list here, see if we can find the carbonate ion.
I see it. There it is. CO3 2 minus.
Very good. CO3 2 minus.
So, what do we do here?
Well, what do we have more of, positives or negatives?
More positives.
So we need more of the negative to balance it out, right?
But that's too much.
Okay, well then let's get one more of the positive.
Now you have more positive. You need more negative.
All right, well, that's not a problem. We just keep going back and forth.
Oh, now it's the same. Now you got 6 pluses and 6 minuses.
Very good. So I see that I need 2 irons for every 3 carbonates. Is that right?
Yeah, I see that.
And notice again, we never include the charges in the resulting ionic compound, right? These are ions with the charges, but they're all compacted together in a 3-dimensional lattice, right? All right, very good. Last one, magnesium phosphate.
I don't see the phosphate ion.
There it is, PO4 3 minus.
Oh, so Mg plus 2 and PO4 3 minus.
That's right.
So, oh, you forgot the 2.
Okay.
Then what?
Well, we have to, what do we have more of?
I think I know the ratio. I think you're going to need 3 magnesiums for every 2 phosphates.
Very good. Mg3, PO4, that's a polyatomic ion. I put it in parentheses too. Now, I want to show you something really quick. It's called the crisscross rule. It's just a little trick that you can use to kind of help you remember what the number of the given atoms that you need to find. And that just helps you find the least common multiple for those values. Another thing that's valuable for, if I give you this compound here, for example, iron 2, let's see, iron, no, let's try again. If I give you, for example, a compound that is iron 3, PO4, 2, right? Then, and I ask you, what's the charge on the iron ion in this compound? You can also do the reverse rule like this, because this will help you identify that the iron must have been a +2 and the phosphate must have been a -3. Right? So you can do that backwards as well. And that helps you with not just the iron, but also identifying what the charge on a given polyatomic ion is.
Okay.
Okay, good. Okay, each of these following metals can form 2 compounds with oxygen. Write their formulas: lead, tin, manganese, iron, and copper. Okay, so we want to know what the 2 compounds that they can form. And this, at this point in our studies, we just have to kind of look in the book and find out what the charges are on these different elements, right? I can also bring up our list in our from class. So here is slide 32 from chapter 3, right? And we saw that these transition metals exist in multiple states. Remember, transition metals are here in the blue, right? And, we'll go gently and gradually trying to figure out what these states are. So you could memorize it if you want to, but it's not terribly helpful because there are others that exist out there. These aren't the only ones. But we can answer this question. Lead forms what kind of ions?
+2 and +4?
That's right. So lead forms a +2, and lead forms a +4. And if it's going to combine with oxygen, what is the ionic, when oxygen is in an ionic compound, what's its charge?
Can you show me the periodic table? Oh, it's going to be a -2.
That's right, because it wants to gain 2 electrons to have a noble gas electron configuration. So for lead, we call it lead-2 oxide when we're talking about lead with a +2 charge. The ratio is just 1 to 1. But for lead-4 oxide, it's 2 oxygens needed, right?
Yeah. So what's the name of that one?
This one here?
Yeah.
That's lead-4 oxide.
But there's only 2 oxygens.
Well, the 4 isn't referring to how many oxygens there are. The 4 is referring to the charge that's on those ions in that compound.
Okay.
Okay, good. So for tin, we can have a +2 or a +4. So that would be the same, SNO and SNO2. For manganese, we can have a +2 or a +3. So for manganese, it would be MnO for manganese 2 oxide. But for manganese 3 oxide, what would the combination, what the chemical formula be for manganese 3 oxide?
Can I use the crisscross rule?
Yeah,
So it's Mn2O3.
that's right, because we can just use those crisscross like that to find out what they are. Good. And what's the name of that chemical?
That's manganese oxide.
But don't you need to put in a number?
Oh yeah, manganese. I can't remember, 2 or 3.
Well, the number is supposed to remind us whether the manganese has a +2 or a +3 charge.
Oh, okay, so it's manganese 3.
Very good. Manganese 3 oxide. All right, iron.
Iron 2 oxide would be just FeO.
Very good. Write that down. Right, because it's a +2 ion and a -2 ion.
Iron 3 would have to be Fe2O3.
Very good. +3, O2 minus, Fe2O3. Very good. This is a -2 there.
Copper is +1 and +2, so that's interesting. Let's think about that. What would that be?
Copper, whoops, not calcium. That's +1, or copper +2. Oxygen is a -2. All right.
Oh yeah, so Cu2O.
Very good. Cu2O, or sorry, whoops, yeah. Cu2O, that's what, copper 1 or copper 2?
That's the one with the +1, so that's copper 1 oxide.
Very good.
And that would just be CuO, copper 2 oxide.
Very good. Okay, excellent job. Okay, so we get to name some compounds here. CaS, any ideas?
Ca, is that calcium?
Yep,
S is sulfur.
very good. So what?
Calcium sulfide.
That's right. And notice how you said sulfide. You didn't say calcium sulfur, right? The last element in an ionic compound always ends in "ide." If it's just an element. If it's a polyatomic ion, then it just ends and the name of the polyatomic ion is used. Okay, so what's the next one?
What's Al?
There it is.
Oh, aluminum. And Br is bromine. Okay, so aluminum bromide.
Very good. Aluminum bromide. Na3P.
Na is sodium. P is what?
Phosphorus.
Sodium phosphorus.
Not sodium phosphorus, but sodium, how do we end it?
Sodium phosphoride.
Sodium phosphide. Good. Sodium phosphide.
Sodium phosphide.
Very good.
Ba, where's that?
Down here.
Barium. As. Arsenic. Barium arsenide.
Very good. Barium arsenide. Excellent.
Rb. Rubidium. Rubidium sulfide.
Very good. Rubidium sulfide. Excellent work. Now, we didn't kind of mention it, but all those previous compounds that we just named were ionic compounds, where you say the name of the metal and the name of the nonmetal. But here we have molecular compounds. Molecular compounds. Molecular compounds, we only say the name of we use prefixes to tell us the number of atoms in the compound. All right, so for this one, silicon. Silicon is not a metal. It's a metalloid here. So we're not going to name it silicon oxide alone, right? It is silicon oxide, but because it's a molecular compound combining two nonmetals, then we're going to call it silicon dioxide. The di is used.
Oh, for 2?
That's right. And this is nice because, we have to remember those prefixes, mono, di, tri. You remember what 4 is?
You said in class Tetris?
Not Tetris, but tetra. That's right, tetra. Okay, so silicon dioxide, what do you think? What's this one?
What's Xe?
It's down here.
Xenon?
That's right, xenon.
Fluoride, so xenon tetrafluoride.
Very good.
Phosphorus, tetraphosphorus decoxide.
Very good. Tetraphosphorus decoxide.
Dichlorochloride.
So you just say, just like this one was xenon, phosphorus, silicon. You just say the whole name of the first one. So it's dichlorine.
7. What's 7?
Hepta.
Hepta.
Kind of like September. Septa and hepta. September used to be the 7th month before Julius and Augustus Caesar added 2 months in July and August. So that's how I remember hepta.
Okay, so dichlorine heptaoxygen.
But not oxygen, right? Oxide.
Oh, yeah. Dichlorine heptaoxide.
Very good. Excellent work. Okay, so we have some ionic compounds again. So there's metals and nonmetals combining, right? But this time, see that these metals, iron, copper, tin, cobalt, those are our transition metals, right? So do you remember what we have to do when we're naming them?
Nope.
Well, we name them just like an ionic compound. So we would say something like iron. This is sulfur, so it goes to sulfide, iron sulfide. But we need to help people know what kind of iron sulfide it is, because iron can form multiple charge states. Do you remember that?
Oh, yeah. Transition metals.
That's right. Usually they form multiple charge states, and so we say iron, and we tell everybody what the charge on the iron is. And do you know what the charge of the iron is if it's combined with sulfur?
No, I don't know how I could tell.
Well, I'll leave the periodic table here, and we'll look at it here. So apparently we have iron with some charge and sulfur with some charge coming together in a 1-to-1 ratio. You see how we see that up here?
Yeah, there's just one of each.
Very good. Now, do we know anything about sulfur?
Sulfur has to have a -2.
That's right. Sulfur forms a -2 charge in ionic compounds. So that means that iron, if it's a 1-to-1 ratio, must have what?
Oh, a +2.
Very good. So that means that this compound is called iron what sulfide?
Iron 2 sulfide?
Very good. And remember that the 2 isn't telling us how many sulfurs or how many irons. It's telling us the charge on that. So that's iron 2 sulfide.
So that's copper 2 oxide.
Very good, because the oxygen forms a -2 charge. Therefore, the copper must be forming a +2.
And that must be tin 4 oxide.
Very good. Tin 4. Why tin 4?
Because oxide is -2.
Yeah, let's write this down so we can kind of see what we're thinking of. Oxide's -2.
And there were 2 of them.
Right, there's 2 of them. And there's only 1 tin.
Yeah, so that had to be a +4.
Very good. So, this one.
Chloride is -1. So, and there's 2 of those. So, let's see. Oh, yeah, cobalt 2 chloride.
Very good. Now, you didn't say the rest of this.
Oh, I didn't see that.
So what do we do? These are called, you remember what that's called when there's some water associated with the ionic compound as it's in its container?
I can't remember.
That's called a hydrate. A hydrate.
Oh, yeah, hydrate. And you just say cobalt 2 chloride hydrate.
Well, you also include the number of waters, which is 6, right? So hexahydrate.
Okay. So copper 2 chloride hexahydrate.
Very good. That's the name. All right. So we have some more compounds to name for us. Nice compounds. All right. What do you think? NaNO2.
Sodium something.
Good. Na is sodium. Very good. Where do we have to look for the NO2?
Oh, that's a polyatomic ion. So do you have that sheet?
Yeah, let's bring out our polyatomic ion sheet, which is just on the back of your periodic table.
Oh, yeah, I got it. Let me look for the NO2.
I found it. Here it is. Nitrite ion.
Okay, so that's sodium nitrite?
That's right. Sodium nitrite.
So next one, K. That's potassium, right? Is it potassium? Yeah, there it is, potassium. MnO4. Permanganate?
Very good. Potassium permanganate.
Okay, and the next one is magnesium sulfate, and then 7 is hexa?
No, 7 is hepta.
Hepta. Magnesium 2 sulfate heptahydrate.
Okay. Now, we didn't need to include the magnesium 2,
But magnesium has a +2 charge.
but it always has a +2 charge. So if you said magnesium 2 sulfate, people would just think, what? But, they would understand what you're talking about. But you don't have to include it because magnesium is a representative element. In other words, these metals will always have a +1 charge if they're in the first column and a +2 if they're in the second. So we only have to use the number, like the Roman numeral in between, when we're dealing with transition metals.
Okay. So magnesium sulfate heptahydrate.
Very good. How about that one?
I need the polyatomic ion list. Thiocyanate.
That's right. Potassium thiocyanate.
Potassium thiocyanate.
Very good. Okay, so we got to name all these, and we want to identify whether they're ionic or molecular.
Okay. Cr, that's chromium.
Very good. Element there, 24, chromium.
Chromium chloride. It's a transition metal, though, so we want to tell people what the charge is. So chromium 2 chloride.
Very good. Now, how did you know it was chromium 2?
Well, because there's 2 chloride ions.
That's right. Cl minus twice. And so the charge on this chromium, because there's only one of them for every chlorine, must be a +2 charge to balance that out. So we call that compound chromium 2 chloride. Very good. Is that ionic or molecular, that compound?
That's ionic. Contains a metal.
Very good. It's easy to tell if it's ionic if it contains a metal. Another way of reminding ourselves that it's ionic is if it is made of ions. I mean, that's in a way an easier way, but it's not always necessarily clear. Okay, so B. What's B?
Sulfur. Oh, those are nonmetals, so that's disulfur dichloride.
That's right, because molecular compounds, we just use the prefixes to tell us how many elements there are of the different ones. And like you ended chlorine and chloride, sulfur, you just said sulfur, disulfur dichloride. Very good job. Molecular or ionic?
Molecular.
Very good. Here?
All nonmetals. That's a lot. Those are polyatomic ions. Okay, yeah, so that's the acetate ion and the ammonium ion. So ammonium acetate?
Very good. No metals, but is it an ionic compound?
It is, because it's made of ions.
Very good. D.
That's a polyatomic ion, I think, but why is there no charge?
Well, if there's no charge, it's not an ion, is it?
Oh, yeah. So is it just, let's see, sulfur is a nonmetal, oxygen's a nonmetal. Is it just sulfur trioxide?
That's right. Sulfur trioxide. Ionic compound or molecular compound?
Molecular.
Very good. E.
KiO3. What in the world? Is IO3 on our list?
It's not on our list.
Is that a polyatomic ion?
It is a polyatomic ion. Okay? And, the list of polyatomic ions, again, is not only on, this is not the only list of our polyatomic ions. So if I come across a polyatomic ion that I don't know, then I just type in here IO3 ion and try to find out what it is. So, iodate ion. Iodate. So this is going to be called what?
K is potassium. So potassium iodide?
Very good. Ionic or molecular?
Ionic. Metal. Has metal.
Very good. F. Ionic or molecular? Let's do that first.
Potassium and oxygen. Just molecular. So tetra potassium hexaoxide.
Very good. EFG. Here we are.
That's calcium SO3. There it is right there. Sulfite?
Very good. Calcium sulfite. No number needed because why?
Because calcium's in the second column.
Very good. All right, next.
AgCN. Silver Ag, right?
Yeah, Ag is down here, silver.
CN. Is that? Oh, cyanide. Silver cyanide.
Very good. Silver is a transition metal.
Oh, yeah. So I got to say silver 1 cyanide because the cyanide has a -1 charge.
Okay, very good. Let's walk through that with everybody at home so everybody understands what's going on there. The cyanide ion has a -1 charge, and we are shown that there's one silver ion for every cyanide ion, so it must have a +1 charge, right? Silver 1 cyanide. Now it turns out that silver is an example of an element that only forms a +1 charge. So because of that, silver, you don't usually call it silver 1 cyanide, but that's not a problem. You can do that.
So there's some that you don't use?
Yeah, it's kind of frustrating, but it's nothing that we're going to test you on. It's just something that you gradually become familiar with. Zinc is another example of a compound that, so silver cyanide's ionic, right?
Yeah.
So let's go on to the next one. Zinc is another example of one that only has a +2 charge. So we don't need to call it zinc 2 bromide. This compound is just called zinc bromide. All right. Last one. What do you think?
Hydrogen and what does Se?
It's selenium down here.
Selenium. So dihydrogen selenium?
Okay, close. Remember that we end in what?
Oh yeah. Dihydrogen selenide?
Very good. Selenium goes to selenide. Excellent work. Okay, so we're writing the formulas for these compounds, right? I'm going to put these periodic table and polyatomic ion off to the right. I'm going to have them. You have them with you, right?
Yeah, I have them.
So you want to be able to refer to them always because they're going to be the way you're going to learn how to begin to name and gradually remember, okay? So I'm going to be using them even though I don't bring them up every time, okay? So sodium monohydrogen phosphate. Is this an ionic compound?
Yep.
What is the chemical formula?
Sodium's Na, and then the polyatomic ion, looking here, monohydrogen, HPO4 with a 3-.
Good. So we want to make sure that we know that Na is going to form a +1.
Oh yeah, it's in the first column, so +1.
And then HPO4 2-, right?
Oh yeah, 2-.
HPO4 2-. Okay, so sodium monohydrogen phosphate. What's the chemical, or what's the ratio? How do these two come together?
Oh, you mean you need 2 sodiums?
That's right. Na2HPO4. We don't show the charges after they're together, right? But we needed 2 of these, 2 Na pluses, for every one of the HPO4. 2-. Okay. Lithium selenide.
Selenide, that's selenium, Se, right?
That's right.
Lithium, Li.
Right. So what are our ions that form from these elements?
Lithium is a +1. It's in the first column. Whoops.
Wrong one. There we go.
Selenide is a -2.
Very good. Because it's in the 6th column, right?
6th?
Well, if you think about this set here and this set over here as our representative elements, we say 1, 2, 3, 4, 5, 6, 7, 8 columns. That's how we number the columns of our representative elements.
Okay.
So what's the ratio?
2 lithiums for every selenide.
Very good. Chromium 3 acetate.
Chromium 3. Chromium Cr.
Very good. Chromium Cr.
And acetate, let's look on that list. C2H3O2 chromium 3. What does the 3 mean?
Oh yeah, the 3 means the chromium has a +3 charge.
Oh, that's good. That's nice to use. So now has to be 3 acetates for every chromium. So Cr, C2H3O2 in parentheses, and there's 3 of those.
Very good. Excellent. Next one, disulfur decafluoride.
That's easy. Di, S2, F10.
Very good. Nickel 2 cyanide.
Nickel 2, Ni with the +2 charge.
Very good. You're getting good at this. Nickel with the +2 charge. That's nickel 2. And then cyanide ion.
That's a polyatomic ion. Let me check. What's Cn-?
Very good.
So NiCN2.
Like that?
Well, you need the parentheses.
Very good. You need the parentheses. Excellent. All right. Iron 3 oxide.
Iron 3 oxide. Fe has a +3 charge, right?
That's right. That's what the iron 3 is telling us.
Oxygen is a -2. That's looking at the periodic table, column 6, right?
That's very good.
So I can use the crisscross rule here, Fe2O3.
Very good. Iron 3 oxide right there. Antimony pentafluoride.
Antimony, where's that at?
That's element number 51.
Oh, Sb?
Yeah.
And penta. Oh, this is a molecular compound.
That's right. It is a molecular compound. How did you know?
Because it says penta in there. And also because I see antimony is not a metal.
Very good. So antimony pentafluoride.
So 5 of those.
5 fluorides. Very good. Excellent job. Here we have some more to work on. Ammonium sulfide.
Ammonium, I know that. That's NH4.
Very good. NH4. Now, do you remember the charge?
Oh, let me look. Okay, it's on the polyatomic ion chart. It says +1.
Very good. Sulfide.
Column 6, that's a 2-.
Very good.
So there's 2 ammoniums for every sulfide.
Very good. NH4, 2 of those, because I need 2 of these +1 charges, right? For every one of those sulfurs.
Yeah.
Okay, excellent. Chromium 2 sulfate hexahydrate. Wow, that's a mouthful.
Yeah, so chromium 3 actually.
Oh yeah, chromium 3 sulfate hexahydrate.
The chromium Cr
Very good.
and the sulfate, let me look.
Always look at your polyatomic ion chart. If you don't know the name of the polyatomic ion, that's how you're going to learn.
SO4 2-.
Very good. That's the sulfate, SO4 2-. Now, what's the charge on the chromium?
How am I supposed to know?
The chromium 3 right there, right?
Oh. So does that mean 3 sulfates?
Well, the chromium 3 essentially is telling us the +3 charge. And it does mean 3 sulfates, consequently here, but that's because the crisscross rule works the way it does. But it's not always going to indicate the number of either the metal or the counterion with the metal. Okay?
Is that it?
Well, not quite. What else do we have?
The hexahydrate. That's 6 H2Os.
Very good. 6 H2Os. Excellent.
Okay, next is silicon tetrafluoride. That's easy. SiF4.
Very good. Molecular compound, right?
Yeah.
Molybdenum, what is that number? 4?
Yeah, 4 sulfide. Molybdenum sulfide. Molybdenum 4 sulfide. Where's molybdenum?
It's element 42.
Okay, so MO.
MO.
The 4 means that MO has a +4 charge, right?
Very good.
And the sulfide always forms a -2. So that's MOS2.
Very good. Because I need 2 of these -2 charges for every of molybdenum 4.
Okay, tin 4 chloride.
Okay, next one, tin 4 chloride.
Tin is what element?
Element 50.
Okay, yeah, so SN.
Very good.
And then the 4 means the +4 charge.
Very good.
And Cl has a -1 charge, but there's 4 of those.
Very good. I mean, there has to be 4. How do we know?
Well, because tin has a 4. So it's SnCl4.
Okay, very good. Tetraphosphorus heptasulfide.
I'm good at those prefixes. Tetra is 4.
For what?
Phosphorus. So P4, S7? Is that hepta?
That's right, 7. Very good. P4S7. Excellent job. Okay, last one. 2 compounds here. This is what you can use for anti-dandruff agents. What are their names?
Let's see. Se What element is that?
That's element 34.
Oh, yeah, selenium. And S is sulfur, right?
That's right.
So selenium sulfide?
Well, almost.
Selenium 2 sulfide?
No, these are molecular compounds, right?
Oh, yeah, both selenium and sulfur are nonmetals. So diselenium hexasulfide
Very good. Diselenium hexasulfide.
and diselenium tetrasulfide.
Very good. Fabulous job. Good job. Thanks for your efforts, Fred.
Yep, no problem.